Welcome back to the deep dive. Today, we are opening up a topic that I think it creates a false sense of security for a lot of people. We're talking about Python.
Mm.
And I know what you're probably thinking. Python, I learned that in a weekend. It's easy. It reads like English.
That sentiment right there, that exact idea that Python is easy, is precisely why we need to have this conversation.
Mm-hmm.
It is, I think, the single biggest trap in modern software engineering.
That's a bold statement. So you're saying the very thing that makes it popular, its user-friendliness, is actually a trap?
It is a trap because it masks an incredible amount of complexity. I mean, Python is famous for being executable pseudocode, right?
Right.
You can write a script in 10 minutes that does something genuinely incredible. But, and this is the key, there's a massive, dangerous gap between writing a script that works on your laptop and engineering a system that can actually survive production traffic.
And that is the exact gap we are trying to cross today. We have a stack of technical guides here, some internal company documentation, performance analyses, and it all focuses entirely on what you'd call professional Python.
Yeah, this isn't a Hello World tutorial.
No, not at all. This is a look at the brutal truths of its performance, the hidden gears of memory management, and really the architectural shifts that separate a junior developer from a senior architect.
We're going to deconstruct the magic. Because while magic is fun when you're learning, magic is, frankly, terrifying when you're trying to scale a business.
Yeah.
You absolutely need to know how the machine works.
So let's start with that machinery then. The source material refers to this first section as the brutal truths. And right at the top, it hits us with performance, specifically the very confusing reality of concurrency in Python.
This is usually the first major wall a developer hits. You know, you come from a language like Java or C++C, or maybe you just have a powerful new laptop. You've got 16 cores. And you think, great, I'll spin up 16 threads in Python and get my work done 16 times faster.
It seems like basic math. It's an intuitive leap. But the source says, just don't do that.
If you do that in Python for any kind of CPU-heavy task, you will not get a 16x speed up. In fact, you might actually make your code slower than if you had just run it on a single thread.
Wait, hold on. Slower? How can throwing more resources at a problem make it slower? That sounds like a fundamental design flaw.
It feels like one, I know, but it's actually a very specific design choice called the GIL, the Global Interpreter Lock. And to understand why it exists, you have to go back to how Python manages memory. At its core, Python is not thread-safe by default.
And thread-safe meaning, if two threads try to grab the same piece of data at the same time, they don't corrupt it or crash the system.
Exactly. More specifically, Python uses a mechanism called reference counting to manage memory. Every single object, an integer, a string, a list, anything, has a little counter attached to it that basically says how many variables are pointing to me right now. So if you have a variable x equals 10, the integer object 10 has a reference count of 1. If you then say y equals x, that count goes up to 2. When it drops to 0, the memory is freed.
Simple enough. So where's the problem?
Now imagine you have two threads running on two different CPU cores. They both try to access that object and change the reference count at the exact same nanosecond. Without some kind of lock, you get a race condition.
One thread's change could overwrite the other one?
Precisely. One overwrites the other. The count is now wrong. And maybe the memory gets freed while another thread is still using it. That's a seg fault. The entire interpreter crashes.
So the GIL is the solution to prevent that crash.
It's a very blunt instrument solution, but yes. The GIL is a mutex mutual exclusion lock that protects the entire interpreter. It effectively says, I don't care how many CPU cores you have or how many threads you spawn, only one thread is allowed to execute Python bytecode at any given moment.
So if I have those 16 threads I spun up, 15 of them are just sitting there, waiting.
They're constantly pausing, waiting for the lock, acquiring the lock for a short time, running a few instructions, then releasing the lock so another one can have a turn. And all that acquiring and releasing takes time. That's the overhead.
So for something like number crunching, calculating pi, processing images, threading adds all this management overhead without adding any real parallelism.
That's it. You get no speed up, just slow down.
That sounds absolutely disastrous for a language that's so dominant in data science and AI. But there's a nuance here, right? The source makes a really big distinction between CPU-bound and I/O-bound tasks.
A huge distinction. And this is where the senior engineers know exactly when to use threads and when not to. The GIL is, you could say, polite. It releases itself whenever a thread is just waiting for input-output.
I/O meaning network requests, reading from a hard drive, talking to a database.
Exactly. Any of those. If your code says, go fetch this web page, the CPU is basically idle, right? It's just sitting there waiting for the server on the other end of the world to reply. In that moment, Python releases the GIL. Thread A goes to sleep waiting for the internet, and thread B wakes up and gets its turn to run on the CPU.
So for something like a web scraper, or maybe a bot that's talking to 1,000 different APIs at once, threading is actually perfect.
It is ideally suited for that. You can have hundreds of threads, and they'll all interleave their work very efficiently because they spend most of their time waiting anyway.
Okay, but let's go back to the heavy stuff. If I do need to process a massive data set on my 16-core machine and I can't use threads, what is the workaround? Do I just have to accept that Python is going to be slow?
No, you have to step outside of the shared memory model of threads. You use the multiprocessing library. Instead of spawning threads, you spawn processes.
And what's the fundamental difference there?
A thread lives inside the same memory space as other threads. They can all see the same variables. A process is a completely separate instance of the Python interpreter. It has its own memory, its own variables, and crucially, its own GIL.
Oh, so if I have 4 cores, I can spin up 4 processes and I suddenly have 4 GILs running in parallel.
Exactly. Now you have true parallelism, but, and you knew this was coming, there is a cost. Because they don't share memory, if you want to send data from process A to process B, you have to serialize it, the term is pickle it, send it over an inter-process communication pipe, and then unpickle it on the other side. That data copying is expensive.
So there's no free lunch. It's a trade-off.
Never. You trade the GIL overhead for IPC overhead. You have to choose which one is less painful for your specific problem.
This talk of memory brings us to the next brutal truth in the material, the way Python handles objects. The source has this section titled, Everything is an Object, which sounds a bit philosophical, but I gather it's actually a serious warning about RAM usage.
It is, absolutely. In a lower-level language like C, if you define an integer, say, an int32, it takes up exactly 4 bytes of memory. That's it. It's just the raw binary data for that number.
And in Python, what happens there?
In Python, x1 isn't just a number. It's a full-blown structure. It's a Pi object. It lives on the heap. It contains the reference count we just talked about. It contains a pointer to its type object, which is a structure that says I'm an integer. And then buried inside all that, it contains the actual value.
Wow. So how big is it, all told?
It depends on your version of Python and your OS. But a simple integer is usually around 28 bytes.
So let me get this straight. You have 4 bytes of actual data and 24 bytes of packaging, of overhead.
Roughly, yes. Now, I want you to imagine that overhead multiplied by a billion numbers in a data pipeline. You can start to see why Python is known for being memory hungry.
Is there any optimization there at all? Or are we just stuck with these fat objects for everything?
Python does have some clever tricks. For example, it pre-allocates and caches small integers. The numbers from meta5 to 256 are actually created once when the Python interpreter starts up. They're singletons.
Wait, really? So if I have 2 separate variables, A equals 5 and B equals 5, they are actually pointing to the exact same object, the same address in memory?
Yes. You can prove this in the interpreter. If you type A as B, it will return true. But if you do the same thing with A 1000 and B equals 1000, Python will generally create 2 separate distinct objects. A as B will be false. This trick is called interning, and it saves a surprising amount of memory for the most common numbers.
That's fascinating. But let's get into the garbage collection. I think most people have this assumption, I don't have to malloc or free memory, so I don't need to know how it works. But the source argues that for high-performance systems, you really, really do.
You do. We mentioned reference counting. That's the primary mechanism. As soon as an object's count hits 0, its memory is freed immediately. It's deterministic, which is great. But there's a fundamental flaw in pure reference counting.
And what's that flaw?
Cycles. Reference cycles. Imagine you have object A, and it has a reference to object B. And object B, in turn, has a reference back to object A.
So they're pointing to each other like a circular dependency.
Exactly. Now, even if you delete every other variable in your program that was pointing to them, A and B are still holding on to each other. Their reference counts will both be stuck at 1. They will never hit 0. They are a classic memory leak.
So does Python just let them leak and consume memory forever?
No, it has a backup plan. A separate system called the cyclic garbage collector. This is a different beast. It's a generational garbage collector that wakes up periodically. It pauses your program for a moment, scans the memory looking for these isolated islands of objects that only reference each other, and then it cleans them up.
Pauses your program. That sounds scary for real-time applications or web servers.
It can be. It's usually just a few milliseconds. But if you've created and destroyed millions of objects, it can cause a noticeable stutter or a spike in latency, We call it GC pressure. In some high-frequency trading systems, senior engineers will actually disable the GC manually during critical loops to avoid that stutter and then re-enable it later.
Wow. Okay, speaking of tuning and optimization, there's one specific feature in the source that I really want to drill into. It's called slots. It's presented almost like a secret cheat code for slashing memory usage.
It's probably one of the most powerful and underused features in the language for performance. To understand it, you have to know how a normal class works. By default, when you create an instance of a class, Python gives it a special dictionary called dict to store all of its attributes.
And dictionaries in Python are hash maps, right?
Right. And hash maps are wonderful, they're fast and flexible, but they are heavy. They pre-allocate a lot of extra space to avoid key collisions. They're designed to be dynamic, which means you can add new attributes to an object at any time, on the fly.
But if I'm building something simple, like a point class with just X and Y coordinates, I'm never going to add a Z coordinate or a color attribute to it later. I just want X and Y.
Exactly my point. So you are paying the memory cost for the flexibility of a dictionary that you absolutely do not need. If you add one line to your class definition slots equals X, you are telling Python, freeze the structure. These are the only attributes this object will ever have.
So what happens under the hood when you do that?
Python throws away the dict. It gets rid of it completely. Instead, it allocates a fixed, compact block of memory, almost like a struct in C that's just big enough for a pointer to X and a pointer to Y.
And what are the savings like in practice?
They can be massive. We're talking a memory usage drop of 40 to 50% per object. If you're in a situation where you're instantiating millions of small objects like in a simulation or a game using slots, is the difference between running on a cheap server and needing a giant, expensive machine.
That really brings us to the summary of this whole internals segment, what the source material calls the glue philosophy. Puts it very bluntly. Python is slow, 10 to 100 times slower than C++ or Rust for raw computation.
It is. It's an interpreted language. It's dynamically typed. It has all this object overhead. It all adds up. But the philosophy of professional Python development is this. Python is not for the heavy lifting. Python is the manager.
The manager.
Think of a construction site. You don't want the site manager physically carrying bricks up a ladder. That's a terrible use of their time. You want the manager coordinating the team, reading the blueprints, and telling the specialized, powerful machinery what to do. Python is the glue. It's the orchestrator.
So when I do heavy math in NumPy or Pandas,
Python isn't doing that math. Python is just making a quick call to a highly optimized C or Fortran function that does the actual work.
so if I find myself writing a triple nested for loop in pure Python to process the pixels of an image,
You are using the language wrong. You are making the site manager carry the bricks. Your first thought should be, how do I vectorize this operation? How do I push this entire loop down into the compiled C layer where it can run 1,000,000 times faster?
Okay, let's move from the internals to the code we actually write. Segment 2, writing scalable code. The source creates this really interesting dichotomy between the junior habit and the senior habit. And it starts with the most common, most basic data structure of all, the list.
The list is just so seductive, isn't it? It's the Swiss Army knife. You need a stack. Use a list. You need a queue. Use a list. An array. Just use a list. It works. But working is not the same as scaling.
Give me the classic example where a simple list just falls apart under pressure.
Using a list as a queue. A first in, first out data structure. The common pattern is you append new items to the end with .append, and you take items off the front with .pop0.
I've written that exact code probably 100 times.
And it's a performance disaster. Because of how lists are stored in memory as a contiguous block of pointers, when you remove the very first item, Python has to physically shift every single other item in that list one spot to the left to fill the gap.
So if I have a list with 1,000,000 items in it,
You are performing 1,000,000 copy operations just to remove one item from the front. That is an ON complexity operation. It gets linearly slower the bigger the list gets. It's a time bomb in your code.
so what's the senior engineer's alternative? What should I have been using all this time?
Collections.dic. It stands for double-ended queue. Under the hood, it's not an array. It's implemented as a doubly linked list of blocks. Removing an item from the front or the back is O1, constant time.
Constant time.
It doesn't matter if the queue has 10 items or 10 billion. It takes the same tiny amount of time to pop from either end.
It's a one-line change in the code, but a completely different performance profile. That's incredible.
It's a perfect example of knowing your data structures. And then there is heap. If you have a problem where you need to keep a running list of the top 10 highest values in a massive incoming stream of data.
A junior dev, myself included, would probably append everything to a list and then sort the whole list every single time a new item comes in.
And sorting is expensive. N log n complexity. A heap, specifically a min heap, which is what HeapQ gives you, allows you to maintain that ordered list efficiently. You push new items in, and the smallest item is always at the top, ready to be popped off if the heap gets too big. It's vastly more efficient for any kind of priority queue task.
Now, this next pattern is labeled in the source material as, and I'm quoting, the single most important pattern in Python, the iterator protocol.
If you take only one thing away from this entire deep dive, learn this. Understand the fundamental difference between a list, which holds everything in memory at once, and a generator, which produces values one at a time on demand.
The scenario they give is a perfect illustration. You have a 10 gigabyte CSV file. Your laptop has 4 gigabytes of RAM.
The junior developer writes file contents, f.read lines. They try to load the entire file into a line of strings in memory. Python asks the operating system for 10 gigabytes of RAM. The OS says no, and your script crashes with a memory error.
Game over.
The senior developer treats the file as a stream. They write for line and f. This uses the file object itself as an iterator. It reads one single line from the disk, puts just that line into memory, you process it, and then, and this is the key, it throws that line away before reading the next one.
So your memory usage stays completely flat.
Flat and tiny, you could process a terabyte-sized log file on a tiny Raspberry Pi using this method. It's all about lazy valuation.
And we can write our own functions that behave exactly like this using the yield keyword, correct?
Yes. The moment you use yield in a function instead of return, you transform that function from a regular subroutine into a generator.
Can you explain the mechanism there? How is yield so different from return?
When a function returns, its job is done. It destroys its entire local scope. All the variables inside it are gone forever. When a function yields a value, it pauses. It freezes its entire stack frame, the complete state of all its local variables, and hands that one value back to the caller.
And when you ask for the next value,
it wakes up at the exact spot it left off with all its variables intact and continues running until it hits the next yield statement.
So it creates this memory-efficient, lazy pipeline.
Lazy is a huge compliment in programming, and you can chain them. You can have one generator that reads lines from a file, which feeds into another generator that parses JSON from each line, which feeds into a third that filters for certain records. The data flows through this pipeline one item at a time. It's incredibly cache-friendly and memory efficient.
The source also points to the itertools module as a powerful companion to this pattern.
Oh, itertools is the hidden jewel of the standard library. It's a collection of high-speed C-implemented building blocks for working with iterators. Things like chain to glue multiple iterables together without copying them into a new list, or ilist to take a slice of a generator without having to consume the whole thing first. These are faster and more memory efficient than anything you could write in pure Python loops.
Okay, let's talk about a classic trap, a bug that I think every single Python developer creates at least once, the mutable default argument.
Yes. The classic interview question. It's a rite of passage.
You define a function, def additum item, mylist. The logic seems sound. If the caller doesn't provide a list, just create a new empty one for them.
It looks completely logical.
Yeah.
But it betrays a fundamental misunderstanding of how the Python interpreter works. The def statement is executable code. It runs once when the module is first imported and loaded into memory, not every time the function is called.
So that empty list, the ls, is created only once.
Once. At startup, that single list object is then attached to the function object itself and persists for the entire life of the program.
So if I call the function once, and I add apple, and then I call it again somewhere else in my code without providing a list,
the second time you call it, the default argument is already apple. You are unintentionally sharing state across completely unrelated function calls. It causes some of the most nightmarish bugs to debug because the function behaves differently depending on how many times it's been called before.
So what's the correct idiomatic fix?
You use a sentinel value almost always. None. The signature should be def atom, item, mylist. None. Then inside the function, you have a simple check. If mylist is none, mylist in smexel. This ensures that a brand new empty list is created every single time the function is actually run.
It feels like a bit of a workaround, but it's actually just being explicit about when initialization happens.
Precisely. It's about understanding the life cycle of objects in Python.
Let's touch on a couple of modern syntax features before we switch segments. The walrus operator.
Right, introduced in Python 3.8. It allows you to assign a value to a variable in the middle of an expression. It's fantastic for cleaning up while loops where you previously had to fetch some data, then check if it was empty on a separate line. Now you can do it all in one go. It reduces boilerplate.
And match case, Python's version of a switch statement.
It's like a switch statement on steroids. It's called structural pattern matching. You aren't just matching simple values. You're matching the shape of your data. You can say things like match a dictionary that has an ID key and also a user's key, which is a list. It makes parsing complex, nested JSON responses so much more readable than a long, ugly chain of if-else checks.
Okay, let's zoom out. We've talked a lot about the language itself. Now let's talk about the ecosystem. Segment 3. The source is very aggressive here. The title is literally Stop Living in the Past.
This is where the landscape has shifted most dramatically, I'd say, in just the last couple of years. If you are still running pip install and just dumping everything into a requirements.txt file, you are, to put it bluntly, doing it wrong.
Guilty as charged. I do that all the time. What is the fundamental problem with requirements.txt?
It's too simple. It's not deterministic. It usually just lists your top-level dependencies, right?
Yeah.
I need Flask version 2. But Flask itself needs Werkzeug, and Werkzeug needs something else. Requirements.txt doesn't strictly lock the versions of those subdependencies.
So I run pip install-r requirements.txt on my machine today, and everything works. My colleague does it next month on a new server.
And in that month, a subdependency of a subdependency has released a new version with a breaking change. Your production server crashes while your laptop still works fine. That is dependency hell. And requirements.txt is a one-way ticket there.
So we need locking. A way to guarantee the environment is identical every time.
You need a lock file, a file that records the exact version and ideally the cryptographic hash of every single package in the entire dependency tree.
The source material suggests two main tools for this, Poetry and the newer UV.
Poetry has been the gold standard for a while, and it's excellent. It manages your project dependencies and publishing, but UV is the new disruptor on the block. It's built by Astral, the same team behind Rough, and it is written in Rust.
There's that word again, Rust keeps coming up.
It's the recurring theme of modern high-performance Python tooling. UV is a drop-in replacement for pip, but it is insanely breathtakingly fast. It can resolve a complex dependency tree in milliseconds that might take pip several minutes.
But why does that speed matter so much for a package manager? I mean, I only run it once in a while when I set up a project.
Do you? In a modern CI/CD pipeline, you might be building and testing your application dozens of times a day. Shaving minutes off every build adds up to hours of saved developer time and faster feedback loops. And UV also manages your virtual environments and can even install Python versions. It replaces pip, pip tools, virtual AM, and PM all in one single fast binary. The recommendation from the source is clear. Switch to UV.
And the cardinal rule mentioned here, which we should just hammer home, never install globally.
Oh, never. If you are typing sudo pip install in your main terminal, you are polluting your system's Python. You risk breaking your operating system tools that depend on it. Always, always, always use a virtual environment. UV and Poetry handle this for you automatically. There's another reason to use them.
Let's look at code quality tools now. Linting and formatting.
The old stack was a bit messy. You'd have Flake8 for style and error checking, Black for formatting, isort for sorting your imports. That's 3 different tools, 3 different configuration files, and they can be pretty slow on a large code base.
And the modern alternative.
Now we have Rough. And again, what is it written in?
I'm going to guess Rust.
It's written in Rust. Rough re-implements the rules from Flake8, Black, isort, and dozens of other plugins, but it runs 10 to 100 times faster. Feels basically instantaneous.
And the source argues that speed isn't just a convenience, it actually changes your behavior as a developer.
It absolutely does. If your linter takes 10 seconds to run, you might only run it before you commit your code. If it takes 10 milliseconds, you configure your editor to run it on every single save. Your code is just always cleaned. It removes an entire category of cognitive load.
What about testing? The classic debate, unit test versus PyTest.
Unit test is built into the Python standard library.
Yeah.
But it's a bit of a relic of a Java-style object-oriented design. You have to write classes that inherit from test case. You have set up and teardown methods. It's very verbose. PyTest is the undisputed industry standard now. It's cleaner, less boilerplate, but the absolute killer feature is fixtures.
Okay, explain fixtures. How are they conceptually different from a setup method?
A setup method is a sledgehammer. It runs before every single test in a class, whether that test needs it or not. Fixtures use dependency injection. You define a resource, say a connection to a test database, as a fixture function. Then, if a specific test needs that database connection, you just list the fixture's name as an argument to your test function. Test user login, DB connection.
So PyTest introspects the function signature, sees the argument DB connection, finds the fixture with that name, runs it, and passes the result into the test.
Exactly. It's explicit and modular. And fixtures can have different scopes. You can have a fixture that runs once per function, once per class, once per module, or even once for the entire test session. You can spin up a Docker container once for the whole test suite, use it in hundreds of tests, and then tear it down at the very end. It's incredibly powerful for integration testing.
There's a really interesting warning in the testing section. Only mock what you own.
This is a deep, subtle point about testing philosophy. A lot of people love mocking. They say, oh, my code calls the Twitter API. I'll just mock the third-party Twitter library. But if you mock an external library, you are making assumptions about its internal workings.
And if that library gets updated and changes its internal logic,
Your mock stays the same. Your tests will all pass, but your code will crash in production because the real world changed and your tests didn't.
so what's the recommended strategy?
You create a thin wrapper around the external service. Make a MyTwitterClient class that you own. Your application logic only ever talks to your wrapper. Then, in your tests, you mock your own wrapper. That way your application logic is tested against a stable interface that you control. And then you write a small, separate set of real integration tests for your wrapper against the actual Twitter API. It decouples your system from the chaos of the outside world.
Okay, segment 4, architecture. This is where we stop looking at individual lines of code and start looking at the whole system. Let's start with the big web development shift, WSGI versus ASGI.
This is the fundamental shift from synchronous to asynchronous web development in Python. The old guard Flask and Django in its standard mode use WSGI, the web server gateway interface. It's synchronous,
Meaning what, exactly?
meaning one request blocks one worker process or thread. If a user asks for a big report and that report takes 2 seconds to generate from the database, that server thread is completely frozen for those 2 seconds. You can't do anything else.
So if my server has 4 worker threads and 5 people all request a slow report at the same time,
The fifth person waits in line. They get nothing until one of the first 4 finishes. It's a classic bottleneck.
and this is where ASGI comes in.
Right. The asynchronous server gateway interface. This is what modern frameworks like FastPI are built on. It runs on an event loop. The best analogy is a single, very efficient receptionist at a busy office. A request comes in. I need some data from the database. The receptionist says, okay, I've sent the request to the DB. Don't wait here. Go sit in the waiting room. Next.
So the receptionist, the single thread, never stops working. It's never blocked, just waiting.
Correct. It can handle thousands of concurrent connections because it's only active when there is actual CPU work to do. While it's waiting for the database or network call to finish, it's busy handling other guests.
But there is a massive, massive pitfall here. The source calls it blocking the loop.
This is the absolute danger zone of async programming. If you have an async function, but inside it you put a heavy synchronous CPU calculation, or you call a library that does a blocking file read, you aren't just blocking that one request. You're blocking the receptionist.
The whole office shuts down.
Exactly. The heart of the server stops beating. Nobody gets served. Every single one of your thousands of current users is now waiting. So in async, you have to be extremely disciplined. Anything that might block must be properly awaited, or you have to explicitly offload it to a separate thread pool.
The source really highlights FastAPI and its companion, Pydantic, as the modern champions in this space.
Pydantic is, and I don't think this is an overstatement, revolutionary. It brings type enforcement and data validation to the runtime. In the past, you'd accept a JSON payload from a user and just kind of hope the age field was an integer.
And if the user sent the string 20 instead?
Your code would probably crash deep inside some business logic 100 lines later with a confusing type error. Pydantic sits at the front door. You define a data model.class user base model.age.int. If the incoming data doesn't match that schema, Pydantic rejects it immediately with a clear, human-readable error message. It sanitizes all your inputs right at the boundary.
Let's shift gears to data science architecture. The source talks about the view versus copy problem in libraries like NumPy and Pandas.
This is a really subtle and silent performance killer. In NumPy, to be efficient, when you take a slice of a large array, say myArray 0.10 NumPy doesn't create a whole new array in memory, it gives you a view. It's just a new object that points to the same underlying memory buffer as the original.
It sounds very efficient, no extra memory used.
It is. But the gotcha is that if you then modify that view, you are also modifying the original data. And that can be a catastrophic bug if you didn't expect it. Conversely, there are other operations where you might think you're getting a view, but pandas or NumPy decides to trigger a copy. Now you've just doubled your memory usage without realizing it.
The source material's advice is be explicit, don't guess.
Yes, if you need a separate copy, explicitly call .copy. In pandas, learn to use .lock for assignment to avoid ambiguity. Don't let the library guess your intent, because sometimes it will guess wrong.
And vectorization. We touched on this earlier.
We did, but it bears repeating. Loops are the enemy in pandas and NumPy. If you find yourself iterating over the rows of a data frame, you have almost certainly failed. You need to think in columns, in entire arrays. When you write df columna plus df column b, that operation is happening down in the compiled C layer, often using special CPU instructions called SIMD single instruction, multiple data. It can process entire blocks of numbers simultaneously. It is literally hundreds or thousands of times faster than a pure Python for loop.
Okay, let's talk databases. The infamous n+1 query problem.
Probably the single most common performance bug in database-backed web applications.
Walk us through it. What does it look like?
Let's say you want to display a list of 100 blog posts and the name of the author for each post. The naive approach is you first query for the posts. Select from posts limit 100. That's one query.
Okay. Then I loop through those posts in my Python code for post_in_posts.print, post.author.name.
In your ORM, object relational mapper, like the Django ORM or Squelchemy, sees that you're trying to access post.author for the first time. It says, oh, I don't have that author DAO loaded yet. So it helpfully runs another query for you. Select from authors, where is ed? And it does this for the first post, and then the second, and then the third.
So I just run 101 separate queries to the database just to render one page.
Exactly. And if your database has even 10 milliseconds of network latency for each round trip, your page now takes over a full second to load, almost all of it just from network chatter.
And the fix?
Eager loading. You tell the ORM up front what you're going to need. In Django, it's select related. In Squelchemy, it's joined load. It tells the database. When you get the posts, also do a SQL join with the authors table. Give me everything I need in one big single query. One query. Done.
Connection pooling is another database pattern that's mentioned.
This is a huge one for production systems. Establishing a new connection to a database is expensive. There's a TCP handshake, authentication, setting up the session. It takes time. A junior dev might write code that opens a connection, runs a query, and closes it, and does that for every single web request.
Which is incredibly inefficient.
A senior dev configures a connection pool. The application starts up and opens, say, 10 connections to the database and keeps them open and alive. When a web request comes in, it just borrows one of the ready-to-go connections from the pool, uses it, and then returns it to the pool when it's done. It's dramatically faster.
Okay, we are entering the final stretch here. Segment 5, the missing manual. This is about advanced patterns and security. We've mentioned Rust a few times, but here the source calls it the nuclear option.
This is for when you've done everything else correctly. You've vectorized your code, you've used the best algorithms, you've optimized your queries, but some small part of your system is still just too slow for your needs. Maybe you're doing real-time cryptography or audio processing or high-frequency trading.
So at that point, do I have to give up and rewrite the whole application in C++ or Rust?
No, absolutely not. That would throw away Python's biggest advantage, which is development speed. Instead, you profile your code, you identify the one specific tiny function that is the bottleneck, just that one function, and you rewrite it in Rust.
How do you actually connect the Python and Rust code?
You use a library called HO35. It handles all the bindings and data type conversions between the two languages, and then you use a build tool called Maturin. You write your Rust code, run Maturin build, and it spits out a standard Python wheel file. To your main Python application, it looks and feels just like any other Python module you installed with pip. You just import my FastTrust module.
But isn't passing data back and forth between Python and Rust expensive in itself?
It can be, yes. Crossing that FFI, the foreign function interface, has some overhead. The trick is to avoid chatty, fine-grained calls. You don't want to call a Rust function inside a tight Python loop where you pass one integer at a time. The right pattern is to pass a large chunk of data, like a whole NumPy array, over to Rust, let Rust do all the heavy, fast looping internally, and then pass the final result back to Python.
And this is how modern tools like Pydantic v2 and Rough are actually built.
Exactly. We are seeing a huge trend where Python remains the high-level, easy-to-use user interface, and Rust becomes the high-performance engine under the hood. It's the best of both worlds.
Let's talk about deployment, Docker specifically. There's a specific myth that gets busted here regarding Alpine Linux.
Oh, the Alpine trap. It's so tempting, and so many people fall for it. Alpine Linux is popular for Docker images because the base image is tiny, like 5 megabytes.
Yeah.
So people logically write from Python, 3.11 to Alpine?
Smaller is better, right, for container images.
Usually. But here's the catch. Alpine Linux does not use the standard C library, glib, that almost all other Linux distributions use. It uses a lightweight alternative called Muscle.
Why does that matter to a Python developer? I'm not writing C code.
It matters because of precompiled binaries, or wheels. When you run pip install pandas or numpy, pip tries to find a precompiled wheel for your system to save time. But those wheels are almost always built for glib. They are not compatible with Alpine's Muscle.
So what does pip do when it can't find a compatible wheel?
It panics and falls back to trying to compile the entire library from its C source code right there inside your Docker build. So your Docker build suddenly needs to download a C compiler, development headers, all this extra tooling. It takes 10 minutes instead of 10 seconds. And the final image often ends up being larger than if you'd started with a slightly bigger base image because of all the build artifacts left behind.
So we tried to save space and ended up wasting both time and space. What's the official recommendation?
Use the slight variants. For example, Python.3.11 on Slim. It's based on Debian, so it uses glib.
Yeah.
Still very small, but it's fully compatible with the vast ecosystem of precompiled wheels.
Okay, security. The silent killers. We absolutely have to talk about Pickle. The source calls it remote code execution as a service.
That's a good way to put it. People think Pickle is just a safe way to save a Python object to a file. But it is not a data format like JSON. It's a protocol for object reconstruction, and that is a critical distinction.
What's the danger? Where's the vulnerability?
The danger lies in a special method called reduce. A malicious actor can create a custom Python class that defines this method. This method essentially tells the unpickler, hey, when you load me, don't just restore my data. To rebuild me, you need to execute this arbitrary function with these arguments.
Execute this function, any function.
Any function you can import, .os.system. They can craft a pickle file that, when you load it, executes rmmorf on your server, or uses curl to download a virus.
And this happens automatically during the loading process.
Yes. The moment you call pickle.load, the malicious code runs. You don't even have to use or inspect the object that gets returned. The damage is already done.
So the rule is, never ever unpickle data from an untrusted source.
Never. If a user uploads a file, or you get data from an external API you don't fully control, use JSON, use mesgpack, use protobuf, use anything but pickle.
One more security tip that honestly shocked me. Assert statements.
Assert is a wonderful tool for debugging. You write assert user.isadmin to state an assumption in your code. If that assumption is false, it raises an error and crashes, which is good during development.
But there's a but.
But Python has an optimization flag, SO. If you run your application in production with python-showmyscript.py, the interpreter strips out all assert statements to make the code slightly smaller and faster.
They just vanish. They're gone.
They're effectively deleted from the bytecode. They don't exist. So if you used assert for your critical security check,
the check is not there in production.
And the door is wide open. The rule is, never use assert for business logic or security checks. Always use a proper if statement and raise an explicit exception, like if not, user.isadmin.raise permission error.
That is genuinely terrifying. Okay, finally, observability. Let's start with structured logging.
Please, stop printing simple strings to your logs. A log line that just says user logged in is text. It's for humans. Computers can't query text easily or reliably.
So what should we be logging instead?
You should be logging structured data, ideally JSON. Use a library like structlog. Your log entry should look like event, login, userid123 status, success. Now you can go into your log aggregator like Datadog or Splunk and ask powerful questions. Show me the login failure rate for user 123 over the last hour.
And distributed tracing.
If you're building microservices, tracing is non-negotiable. Use a standard like OpenTelemetry. It attaches a unique trace ID to an incoming request headers. As that single request jumps from your load balancer to your Python web service to a database to a Redis cache, that same ID follows it everywhere.
So when a request is slow, I can see exactly which part of the journey was the bottleneck.
You can see the whole waterfall diagram. Oh, it spent 10 milliseconds in the Python code, but then it spent 2 full seconds waiting for a response from the billing microservice. Without tracing, you were just guessing in the dark.
We have covered a massive amount of ground. From the deep mechanics of the GIL all the way to the security flaws of Pickle. Let's try to bring it all together in the outro. What is the core senior mindset that the material points to?
I think it comes down to visualization. A junior developer sees code as text on a screen. A senior developer visualizes what's happening in memory. They see the heap, they see the stack, they see the network cost of a database call.
They understand that Python as a language is expensive, so they use it sparingly and for the right tasks.
Exactly. They value simplicity. They prefer composition over complex inheritance hierarchies. And they trust nothing. They validate everything at the boundaries of their system with tools like Pydantic.
And what about the future? The source talks about a polyglot future.
The expert engineer isn't just a Python developer. They are a problem solver who happens to be using Python today. If Python hits a performance wall, they aren't afraid to pick up Rust and write a small extension. They understand that Python's true power is as the orchestrator. It's the brain that manages the database, the cache, and all the other specialized services.
Its development velocity is its killer feature.
Absolutely. Hardware is cheap. Your time, a developer's time, is expensive. Python lets you move fast. And if you know these brutal truths we've discussed, you can build systems that are also fast enough to handle the world.
So here's our call to action for you listening. Don't just nod along with this. Go and actually audit your own code. Open up your project. Check your requirements.txt- is it time to finally switch to UV or poetry? Check your Docker files. Are you falling for the Alpine trap?
And look at your loops.
Yeah.
Can they be generators? Can they be vectorized? Is there an N+1 query hiding in plain sight?
And a final thought for you to chew on. If the most exciting performant tools in the modern Python ecosystem tools, like Rough and Pydantic, are all being rewritten in Rust, are we slowly moving toward a future where Python is really just a thin, user-friendly control layer over a Rust core?
We might already be there. We just haven't fully noticed yet.
Thanks for diving deep with us.
Always a pleasure.
See you on the next one.